Okay, now with a clear understanding of how activities manifest as something to consider due to changing chemical behavior for systems containing ions, all right, we're going to do some examples together. Okay, and so we're going to do an example from your book first. And this example from your book, it uses the Huckel theory. Okay, so I want you to be able to do problems both ways. So not only reference that table that I gave you, but also to be able to use the Huckel theory. And I'll explain how to use it, and then also like my expectations for your quiz and your homework involving the Huckel theory use as we go. All right. The first thing that we do though is we kind of approach the problem in the same way we would with general chemistry, which is why we learned all the stuff that we did last week. We have an acid, we have acetic acid. So AC stands for acetate, so this is HAC. So we have an acetic acid solution. What we'd like to know is the concentration of H plus and the pH, all right, for this solution. We start off by writing the acid equation. We're gonna, excuse me, we're gonna be given a Ka for this reaction. That's 1.74 times 10 to the minus 5. That's the Ka. For any acid equation, you're going to write the acid reacting with water to make H3O plus and the conjugate base. So just remember that from general chemistry. Whenever we're using a Ka, it's always the same looking equation, right? We're going to build an ice table because an ice table still is going to organize our concentrations. We still get rid of an H2O because we know the liquid has an activity of 1. And that's the assumption you're allowed to make here. Okay, we're given an initial amount of HAC. That's 0.100. There's essentially no H3O plus to start, right? There's 1 times 10 to the minus 7, right? But we're going to say that that 0 is really small. And there's no AC to start. Do Q versus K. Q equals 0. Q is less than K. So we're moving in this direction. I'm going to put a minus X here, plus X, plus X. 0.100 minus X, X, and X. Okay. The first step when we do the Huckel theory is to kind of finish the problem like you would in general chemistry. And what we're going to do is we're going to do an iterative scheme to actually get a better estimate for the things we're trying to calculate regarding the concentration of ions in solution. So what do I mean by that? Well, if we go to write a K for this, we know we would normally write our Ka is equal to H3O plus concentration at equilibrium, AC minus concentration at equilibrium, divided by your concentration of HAC at equilibrium. What we also know, though, is that in actuality, for these systems with ions, we should give it the opportunity to actually require activities instead of concentrations. Now, it might turn out that this is dilute enough where, okay, we see that our results aren't really changed that much with actually approximating activities as concentrations. But like I said, let's kind of give it the ability to maybe see if the activities can change our answer. Let's rewrite this in a more appropriate way. The activity of H3O plus, which I'm just going to write as the activity of H plus. The activity of acetate divided by the activity of HAC. That's the real Ka. Keep this ice table handy. We're going to use it. Now, I mentioned what we do iteratively because if I look at this initial mathematical expression that I have, I know that these activities for ions, I really should replace them. This really should be the concentration of H plus times gamma for H plus times the concentration of AC minus times gamma for AC minus over, all right, the concentration of HAC times gamma for HAC. Now your book likes to rearrange this at this point, right? And write this as concentration of H plus, oh, I know that from my ice table. Concentration of AC minus, know that from my ice table. Concentration of HAC, I know that from my ice table. And then group your gammas over here. You don't have to do this, but it is a nice little organizational step. Now imagine we don't have these tabulated values. right? And we really don't even have a guess about what they would be right yet, right? What we would have to do is we would have to implement a Huckel theory. Before we do that, everybody see this gamma down here? Is this species charged? And the answer, hopefully, that you can see is no. So for these situations where we do have an aqueous species but it doesn't have a charge, it's not like we can make the same arguments that it's going to affect things in a drastic way, okay? It's not really going to interact with the pluses and minuses except for weak van der Waals interactions. And so all those arguments we've been making, they don't really matter here. For this, for systems without a charge, right, or species in our system that do not have a charge, we can assume that their gamma is equal to 1. So the real analysis that we're going to enact is all about this Ka is really equal to the concentration of H plus, the concentration of AC minus, over the concentration of HAC, but these two things might have some deviation from ideal behavior, so we have to include gamma H plus and gamma AC minus as well. So whenever you have to use the Huckel theory, here's what you do. You do it iteratively, which means that you guess a gamma to start. And you're going to guess gamma is equal to 1 to start. Okay. Now, remember what your book does. When you use the Huckel theory, gamma for the positive object would be this. Gamma for the negative object would be this. All right. What this implies is that this guy is equal to 1, and that means that both the positive and the negative species are 1. That's where you start. So our Ka at this point is H plus. You essentially assume an ideal solution to start to get an idea of what these concentrations are, because we really have no idea what the ion concentrations are at this point. So you start with an ideal solution. And that'll be nice because then we'll be able to compare it to, right, whatever results we get here, we'll be able to compare it to the non-ideal results when we actually include better versions of gamma. So it'll be really great. I can tell you're excited about it. So here's what we're going to do. We're going to put 1.74 times 10 to the minus 5 over here. My concentration of H plus from the table was X. My concentration of AC minus was X. So I'm going to have an X squared on the top. All right. This was 0.100 minus X on the bottom. And this is a great opportunity to use the 5% rule, which again you analyzed last week. You can solve for X at this point, and I'm not going to do the math. You're going to fill in the math for me. Make sure that you check it. What I get for an X is 1.31909 times 10 to the minus 3. That is my concentration of H plus, which means that that's my concentration of H3O plus. And if this was general chemistry and we weren't considering any effects from activities, we could calculate a pH. So an estimate for the pH would be the negative log of this value, negative log of the unrounded value. And so a good estimate for the pH is 2.8797, but there would be 3 significant decimal points. So we do see that we get an acidic pH out. We used our 5% rule. We should enact a 5% check. The 5% check ends up working. If you get a number that doesn't make sense, remember that you probably used the 5% rule when you shouldn't have. Okay? So now this is exactly what you would do in Gen Chem. So what you do now is you go back. Remember how we said gamma was 1? Right? Now we actually have concentrations in solution whereby we can calculate an ionic strength. I know about what those concentrations are now. This is like the first estimate for those concentrations of ions. Because remember, your X is your H plus concentration, and it's also your AC minus concentration. So now I can use this, calculate an IC, and get a better version of gamma. So the next step is to use that concentration. I'm going to keep it down here. And let's get an IC. And then we can use the Huckel theory to calculate a better gamma. So get IC based off of this first estimate. Well, if you think about how we calculate IC, we have to consider 1/2, what ions are in solution? Well, we have a positive 1 ion, and so we need to take that and square it and multiply by the concentration of H+. We have a negative 1 ion that we can square and it becomes a positive 1, and then we also have the concentration of AC- we have to consider. This is one of those nice situations again. Oh, what was the concentration of H3O+, right? The concentration of H3O+ was our X. What was the concentration of AC- for this problem? Right? You always have to check. It's not always this simple. But for this problem, it was this X as well. So in the context of our previous result, we get that IC is 1/2 of X plus X. So our IC is 1/2 of 2X. Our IC is equal to X. Right? That's our IC. So now we have an ionic strength. And so what we can do is we can get gamma plus minus. Right? Now remember with the Huckel theory, there's that limitation that you get gamma plus and gamma minus and they're the same. In actuality, they probably wouldn't be. All right? We'll actually kind of explore that a bit in the next example. But I can now take this and I can go, okay, the natural log of gamma plus minus is equal to minus 1.173. What charges are in solution? A positive 1 and a negative 1. But we take the magnitude of those at the end anyway, so that just kind of goes away. IC is X. So I could write this as IC to the 1/2, and you actually know what X is in terms of a number. You can put that number there. I'm just going to write this as X to the 1/2 over 1 plus X to the 1/2, because then I can kind of organize it better in my calculator. And so just plug in the numbers. Everything on the right-hand side is known now. We're going to have to use an E to get rid of this natural log, but when you do that math, and because you're going to be doing this for homework and for your quiz, just make sure that you practice doing this. What I get for my gamma plus minus for this problem is I get a gamma plus minus that's equal to 0.959724 via the Huckel theory. Okay? Is it 1? No. And remember, that was our first guess. So if the Huckel theory is valid, if we're in that range where it's good, then this is actually going to definitely apply a correction to our math. Because our first guess for gamma plus minus was 1, and now our next guess is actually, it looks more around 0.96. Now we're going to use the unrounded version, but you kind of get the idea. So we go back to where we made gamma plus minus 1, and we solve for a better X. Right? So we had this expression that was 1.74 times 10 to the minus 5, which was equal to the concentration of H3O plus, concentration of AC minus, over the concentration of HAC times gamma plus, gamma minus. You could use these as superscripts or subscripts, it really doesn't matter. Well, you know what gamma plus is? It goes there. You know what gamma minus is? This goes there. So everybody understand that idea. Gamma plus is that number, and gamma minus is that same number. That's what the Huckel theory tells us. Okay? So now when I do this, I get 1.74 times 10 to the minus 5 is equal to X times X, 0.100 minus X. This looks like the exact same setup, except now I have gamma plus times gamma minus, and when I do that math, I get 0.9210703. So this is a different equation, right? It looks the same functionally, but over here this used to be 1, and now it's that value. So now when you solve for X, you're going to use the 5% rule again, you actually get a different number. And so again, I'm going to give you what the X is, but practice the math yourself. Let me know if you find any mistakes as always. I get 1.374444775. You don't need that many decimals. All right, times 10 to the minus 3. So if you look at what happened to X, our old X, if you remember, was 1.31909. What happened to x? It actually went up, right? Why does that make sense, right? Remember what this reaction is, right? It's an equilibrium. Let me just write it down again and why it makes sense that this x went up. Okay. It's not a strong reaction like our last video. Why do we expect to get actually more H3O plus in solution when we consider the activity? Remember, these guys in solution, they actually feel each other, right? And, right, they're going to influence each other's ionic sphere so that this is not just pure H3O plus and this is not just pure AC minus floating around, okay? Other H3O pluses are going to get in the way of H3O plus. And other AC minuses are going to get in the way of AC minus, right? And so what ends up happening is this recombination, it doesn't happen as readily as if, all right, everything was purely dilute and ideal. There's enough pairing of ions that prevent this exchange. There's enough sort of interference of each other that prevent this exchange occurring where you get more concentration of H3O plus than you would originally expect if you just considered concentrations. Okay? That sounds a lot like what we said before when we had just other ions in there, but that screening and influencing of ionic atmospheres, it can happen even with like itself. One species can be influenced by other species of the same type there. So our X goes up, okay? So this is a molarity. This is our concentration of H3O plus. This is our concentration of H plus. It means the same thing. Our pH we can now calculate. It looks like the negative log of activity, which is our X times our gamma plus. Because remember, gamma plus was referring to the gamma for H3O plus. Now, when I calculate the pH, it actually doesn't look like it changes all that much. I get 2.879725, which doesn't change much at all relative to our old value. This also makes sense, though, when it speaks to the limitations of Debye-Huckel theory, right? Remember what Debye-Huckel theory says, that the activity of H3O plus and the activity of A minus, or AC minus, they are definitely not going to be ideal in this case, but the effects of considering pluses and minuses in solution are the same. The activity coefficients are the same. So if you think about the eventual effects on activity, there's just as many pluses and minuses in solution. They're having a similar effect, so they kind of wash out in terms of the actual chemical activity. There's a bigger concentration of H3O plus, sure, but in terms of activity, it's seeing about equal amounts of pluses and minuses relative to just concentration. And so what you get is a similar pH. This is different than what the book shows, and I think the book does it wrong, okay? Activity is definitely what we need for pH. Your book will just put concentration there, and that's wrong, okay? I'm telling you the correct way to do it. And it makes sense that we get the same pH because the activity, even though the concentration changes, and it's good to know why the concentration changes based off the last argument that we had. The concentration changes, but the activities, all right? Especially the activity of H plus, right? And then inferring that the activity of AC minus, the activities haven't changed to cause any appreciable change in pH. Okay? This is where you would stop for a problem for me. What your book will say is, hold on a second. You now have a better X. So guess what you can do? You can iterate through the process again. If you have a better X, you have a better IC, you can get a better gamma. If you have a better gamma, you can get a better X. If you get a better X, you can get a better IC, get a better gamma, and then you just keep that process going again and again and again. For me, for homework, for your quiz, you would stop after one iteration because that tells me you know how to do it. But for problems in your book, for example, problems that you'll see in your book, and for homework problems inside your book, you'll see that they kind of want you to crank through this until you get a consistent X, a consistent result. Okay? So this is how you use the Huckel theory. Okay? So try to really see what's going on here. Remember, these physical arguments at the end are really important. Yeah, it makes sense we get a higher concentration here because there's some screening stuff going on. We don't get these guys to visit each other in the reaction way as much as we would expect, so we get a higher concentration of that. But the solution has about the same activity because when we consider the pluses and minuses, the effects of plus and minus in the context of the Huckel theory are the same. So those effects mean, all right, that what you get is the same pH out at the end, okay? Higher concentration of acid, but the same pH, okay? Next time we'll do another couple examples where we actually look at using our table, but using the Huckel theory is definitely something I'll ask you to do.